SwayamPrabha. Digital India. Educated India.
Hello friends, in your previous lectures and experiment you might have seen how to calibrate control surface, how to measure center of gravity, and what were the relationship between deflection of control surface and voltage. So now today we'll be seeing an experiment how to collect data from FDR. As it is a very common name, FDR means flight data recorder. In aircraft you might have seen while analyzing how the aircraft was behaving, you need to have data for different deflections as well as measurement of your angle of attack, side slip angle, also whatever the pitch rate, roll rate, yaw rate, and what were the value of thrust, everything is accumulated or combined in flight data recorder. The diagram for flight data recorder is same. In our case we are using an NI module for which we have, this is an NI module, number is 9205, and for this it has a 32 channel analog input module. This is a 32 channel analog input module from which it accumulates data from sensors. This is accumulated from sensor. Now as you know, this requires a power supply. And your data output will be on a PC / laptop, any output device which you want. And this whole part is known as your flight data recorder. The output will be displayed on your laptop, or simply you can call this as black box. Now earlier experiments we showed what were the deflection of control surface with respect to voltages. Now flight data recorder, we have to do the analysis of whole aircraft. So it has to has much more data as compared to a simple experiment which you did for calibration of control surface. The various data which we get from flight data recorder, our flight data recorder are alpha, beta, that is angle of attack, side slip angle, your PQR, that is roll rate, pitch rate, yaw rate, AX, AY, AZ, that is acceleration in X, Y, Z axis, plus you have measurement of pressure, your absolute and differential pressure, your battery voltage, in our flight data recorder we are having different, we are calculating or we are recording different data which are as follows: your angle of attack, your slide slip angle, roll, pitch and yaw rate, your acceleration in different axes, what will be deflection of control surfaces, which you have already seen in previous experiments, what are the total pressure and differential pressure. This can be determined using pitot. What are the values of your roll, pitch and yaw angle? As you might have studied in your aeronautics course, you can determine the relation between your roll, pitch and yaw angle using Euler equation. These were the data we are determining in our flight data recorder. Apart from these, there are several more data if you go for UAV operations, such as your GPS data, which involves your lat, longitude, what will be the height, and magnetometer readings, your even battery voltage, because in UAV operations battery voltage are very important. And for determining, we'll be discussing all this sensor in detail in coming topics. We'll be seeing in our experiments how to derive the flight data, how to derive various parameters using your flight data, and we'll be also showing us small programs, how to get readings from various sensors. For instance, these values can be derived from IMU. We'll be showing a small code. We will be even sharing you that small code so that you can also access that, how to determine your readings of this sensor data. And while performing experiment, we'll be explaining more about these sensors, what are the roles of this, what is accuracy, how to select a particular sensor. That part we'll be explaining in your experiments. Hello friends, during the lecture we discussed about flight data recorder and what were the instruments or sensors we used to accumulate data from our aircraft. Now as you can see in this video, this is the flight data recorder we are using to accumulate data while performing experiments. Now during the lecture we saw the block diagram of flight data recorder. Now I will be explaining you what are the parts which we explained during the lectures. During lectures we said all sensor data are accumulated into or collected through your NI DAC. So this is your NI DAC. We said we are using 16 channel. We are using 16 channel in NI DACs. So these are your 16 channels where the data are collected, and these data are corresponding to different sensors. So as you can see, this is your IMU. As you can see, this is your IMU. Now IMU stands for Inertial Measurement Unit, and it's basically a collection of your accelerometer, gyrometer and your magnetometer. Now as far as accuracy is concerned, your IMU, the acceleration or it can measure is up to 4G, plus minus 4G, with an accuracy of less than 0.5 G. As far as concerning regarding your roll and your pitch angles, it can go from minus 180 to 180 degree in case of roll, whereas for pitching it can go from minus 90 to 90 with an accuracy of less than 0.1 degrees. And as far as heading is concerned, same, it can go from minus 180 to 180 degree, and same your resolution is less than 0.1. This is as far as concerned related to your IMU. And you can see there is a pressure sensor, and you can see in this FDR there are two probes, 1 and 2. This is corresponding to your absolute pressure and differential pressure. Now these two probes will be connected to probes of the aircraft, and corresponding to that you will be getting an absolute pressure which is used in during using this sensor, and a differential pressure which will be used. This sensor will be using both absolute and differential pressure. We'll be explaining in coming lectures what are the use of this absolute and differential pressure to calculate your parameters of aircraft or different input data, you can say, for instance, like height and velocities. We'll be seeing that in coming lectures. And as you can see, all these flight data recorder instruments required a power supply. That's why you can see we have given a, as you can see, for this whole data accumulation, each sensor requires a power supply. That's why we have given a 12-volt battery as a power supply source, and different sensor will be having different power rating. For instance, suppose my IMU will be requiring 5 volt to 10 volt, for instance, I'm saying, then this voltage will be regulated by some BEC or some potential divider, you can say, means voltage will be regulated so that your instrument doesn't get damaged. Now once these whole sensors are accumulated into your NI DAC, then we saw in the block diagram that from NI DAC you can see the output of that particular sensor using some interface or some software. So we will be using a simple LabVIEW code to see what will be the outputs of your sensor, and the results will be shown in your LabVIEW code. Now once the data has been accumulated using your NI DAC, you can see output of particular sensors and parameters using particular sensors using a LabVIEW program which we are using. Now this is the interface we are using to collect data from your flight data recorder. It has different windows corresponding to different outputs which you want to see. For instance, you have readings for acceleration in different direction, x, y, z, your deflection of control surface, that is elevator, rudder and aileron, as well as your pitch, your and roll rates, as well, and also you have value of static pressure and what is altitude. Now this is a simple interface where you can select which particular NI DAC you are using, and the refresh rate, or you can say for this flight data recorder, is 60 Hz. As you can see, while I tilt my flight data recorder, the values corresponding to particular sensors, you can see that pitch, yaw and rate, there you can see modification, as well as you can see variation in acceleration. So while performing experiment, this flight data recorder is kept in your aircraft, and your pressure probes are connected to your flight data recorder, and once a particular maneuver or a flight, normal cruise flight is flown, or corresponding to that, you can change maneuver title, and corresponding to that you can save data. For instance, if your aircraft is performing climb mode, just you have to enter maneuver title as climb and click save, and that data corresponding to climb will be saved. Now after required number of data, suppose you want to perform another maneuver, say instance you want to go for cruise, then type in the title cruise and just click anywhere else. Now these data corresponding to cruise will be saved. So this is a simple software corresponding to your sensors from your flight data recorder. We'll be discussing more about how these sensors work and what are the refresh rate and accuracy of different sensors. We will be sharing you small codes with different sensors, so that also you can be familiar with this sensor, and it will be helpful for you realizing how to acquire data using your MEM sensors. Now why these headings are required? Because suppose while you are trying to build an autopilot and you want to have a particular restriction on particular turn rate, climb rate, and you have limitations such as your servo cannot go beyond a certain limit or certain degrees, you want to have you want to design such as sizing should be enough so that your restrictions can be met. So that's why while performing in manual mode, you have to collect these data, and based on these data you can direct your autopilot to give this much percentage of gain when performing that maneuvers.
In the lectures, we have seen what is a flight data recorder, what are the different parameters which were measured through flight data recorder. We saw a block diagram how flight data recorder works, which consists of how sensors were integrated to an IDAC, and how it was interfaced using a LabVIEW code. So once everything is planted or everything is put into its place, now FDR is put into your flight. And as we have seen in the lectures, how FDR is operated or how LabVIEW program works, after closing that application, you'll get a file which represents all the data you collected for different sensors and for different maneuvers. So here's a test file. We'll open it using Notepad application. This is a test data for Hansa. It, as we told you, it consists of 16 different data. These are mentioned here, and it represents in what particular order the following data will be captured. Hence, this column will represent angle of attack, and respective columns will be in what will be the respective columns. Now, these are the calibrated values. We have already seen experiment how to calibrate a control surface, what do you mean by reference point, and how to calculate slope and your intercept. Now we have shown while recording data from flight lab, you have to just mention which particular maneuver you are performing, and your data will be started from that particular point. Here you can see as the plane was first performing a diving maneuver, and these were the different data which were collected at a sample rate of or scan rate of 1000 hertz. Now these values, see, as you can see, it was in a diving state, so it did not have any y direction acceleration. It wasn't, and these were the data rates till now diving maneuver was performed. Now further scanning this data, you can see for different maneuver. Let's see, once we were in cruise flight, your maneuver title was changed to cruise, and these are the data for cruise flight. And further, these are the data corresponding to climb maneuver. Now when when the students go for experiment performance, for performing experiments, you get these data from FDR, or you can collect it manually also, but these are more accurate because collecting manual data will involve instrumentation error, will involve human error, plus they will have different perception to different readings. Plus, using this data, you can analyze, as we told in lectures also, what are the limitations you want to have if you do want to design autopilot. What value this manual flying you can access that my aircraft has this particular restrictions. For instance, a plane can go perform a roll rate or perform a banking angle to a certain degree. So that particular values will be represented in FDR, and based on that you can design a control system, that how much do I give particular uh, control logic so it doesn't go beyond that saturation point. So based on these data, as you can see, you can analyze how your aircraft is performing. Now for instance, we saw different maneuver title, like you might have seen in previous lectures. We had a experiment to calculate what will be the drag polar of a particular aircraft. So it involved in cruise as well as in climb state. So for cruise, you will go for the data which you got for cruise maneuver. These are the data: angle of attack, slide slip, elevator angle, and different data for cruise mode. And while climbing, you have to go for data in climb mode. Similarly, in order to calculate rate of climb, also you have to see what are the data for rate of climb, and apart from this, what are the mass, manifold pressure, and everything that is manufacturer given. Using that data, you can calculate what is your drag coefficient for a particular plane, or rate of climb, maximum rate of climb. So that's why these data are very much important or aerodynamic point of view of an aircraft. In coming lectures, we'll be seeing how to estimate parameters of a aircraft.
Thank you.